Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about the introduction to proofs. Every deductive subject, math especially I suppose, begins with undefined terms. You might wonder, how do these terms have meaning if they're just undefined? And the answer is, we're going to have axioms, sometimes also known as postulates. These axioms are relationships between the undefined terms and these relationships are assumed without proof. So every subject that is deductive in nature begins with undefined terms, and then the relationships between those are given by axioms, and these are assumed without proof. To develop the deductive system further, you define new terms in terms of the old, and then you discover new relationships between these new terms and the old terms using what are called theorems. So we define new terms, and then we have theorems. We discover relationships between these, and these are always proved. They must be proven, or else we don't think of them as being a relationship at all until you can actually prove that that relationship holds. This idea of a deductive science that begins with undefined terms and simple relationships between them, this goes all the way back to Thales of Miletus. About 550 BC. As a wealthy merchant, he decided what better to do in his waning years, his retirement, than to study some mathematics. So he went to both Egypt and Babylon. And in order to learn the mathematics that had been discovered at that time in those cultures, he had to sign up in various religious cults. The only people who knew how to read and write were the adherents to the various cults. And so they were the ones who propagated all knowledge. So he did that, and he actually impressed his teachers pretty amazingly from some of the things that he did, determining the height of the Great Pyramid in Egypt, for instance. But he came back to Miletus when it was all over, a little bit disturbed because many of the relationships and formulas that he had learned worked only for a certain range of values, but not beyond. They worked for a particular purpose, but if you tried to apply the same formulas for some other purpose, they wouldn't work. So he was a little concerned. He knew that these formulas were defective in certain ways. He felt that one should start with very simple relationships that you could assume everyone could agree upon. For instance, all straight angles are equal. Okay? If I have another straight angle, it's also going to be equal. If you have two intersecting straight angles, Thales discovered that a plus b adds up to a straight angle, and that has to be the same as b plus c, which adds up to a straight angle. If you then subtract b from each side, you get a equals c, which is the theorem that vertical angles are equal. So he started with something very simple, the axiom that all straight angles are equal, plus this principle that you can subtract the same amount from both sides of an equation and preserve equality. And from these principles, he was able to discover the theorem and prove this theorem in this way, that vertical angles, angles that are attached at a vertex from two intersecting lines like this, are always equal. So let's review this process. You need undefined terms. You need assumed relationships between the undefined terms that actually give them meaning. You can define new terms, and then you discover new relationships and you have to prove them, as Thales did. But that implies that you must have some assumed logic. So underlying all of this program is logic. You can't get off of this first base here of undefined terms and axioms unless you have some kind of logic by which you can deduce the truth of propositions. And so we're going to study a little bit more depth, proof and logic. We'll begin with some definitions. A theorem, also sometimes known as a proposition, is a statement that may be shown to be true. You can prove it. A statement that is open to proof. So an example of something that would not be a theorem would be, I feel warm. Well, how I feel is not something I can necessarily prove. And also, any interrogative sort of statement, like, are you feeling well? It's a question. It can't be shown to be true or false. It's just an inquiry. So that's not a theorem. A theorem is a statement that can be proven true. How do you prove the theorem true? By a proof. What is a proof? A proof is a valid argument showing a theorem to be true. We already have some valid forms of argument like modus ponens and modus tollens, and there are other forms as well. So we know about valid arguments and how to construct some of those. What is a lemma? It is a theorem used to prove other theorems. So it's a type of theorem. A corollary is a theorem that is a direct consequence of another theorem. Sometimes you will have a broad theorem. You can see certain special cases that you can identify, and you write those out as corollaries to the other theorem. A conjecture is a statement proposed as a theorem but not yet proven. So until you prove the conjecture, it remains just a conjecture. Once you have a proof, it becomes a theorem. And we often arrive at conjectures through various explorations of our environment or various experiments, and we come up with an idea. So an example of a conjecture might have been at some point the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse length. This, sometimes referred to as the Pythagorean theorem, but this relationship was known for at least 1,000 years before Pythagoras was born. However, it is believed that Pythagoras was the first human being to have given a proof that this relationship is true for right triangles. And so he gets all the credit. It's called the Pythagorean theorem, not because he figured out that this relationship may or may not be true as a conjecture. It remained a conjecture for 1,000 years before Pythagoras, but because he provided an actual proof. And then it became the Pythagorean theorem. That's the way it is in mathematics. The one who gets the credit is the one who provides the proof. A convention is an arbitrary choice. Where's the boundary between blue and purple on the light spectrum? Light has a continuous spectrum. You can have any frequency along a whole range of real values. And so where's that dividing line? Well, it's arbitrary. We can arbitrarily draw a line and say that's the boundary between purple and blue. But who's to say that you don't dice the blue spectrum up into a whole bunch of different arbitrary zones as well, light blue, navy blue, etc. And so these are all conventions. Conventions are based on an arbitrary choice. All mathematical notation is conventional. So it's based on someone's arbitrary choice, which means it's impossible to deduce a lot of mathematics because much of it is conventional, just an arbitrary choice that was made in terms of the notation. But if you want to communicate to someone that you are wearing a blue shirt, let's say, you're talking to them on the phone, say you want to coordinate colors, you say I'm wearing blue, they'll know what you mean, even though the boundaries between the different colors are arbitrary. So this conventional knowledge is very useful in allowing us to convey meaning to each other, even though it is based on something that is completely random or arbitrary. One of our conventions in terms of proof is we often do not write universal or existential quantifiers when they are implied anyway. So let me give you an example. If x is greater than y, and x and y are both bigger than or equal to 0, then x squared is bigger than y squared. So if you have a couple non-negative numbers and one is bigger than the other, then the square will maintain the direction of the inequality. What we really mean is, for all x and for all y, x greater than 0, x greater than y, and x and y bigger than or equal to 0 implies x squared is strictly greater than y squared. We've kind of not written these universal quantifiers, even though they are kind of implied by this statement, that this statement should be true for all x and for all such y. The proof of this theorem isn't complete until we can show that this implication will be true for all such x and y. It's not sufficient to prove it by some specific example. One example might be x is 2 and y is 1. 2 squared is 4, 1 squared is 1. 4 is bigger than 1. Okay, that's fine, but you need to show it's true no matter which x and y are being used. What is a direct proof? of statements of the form P implies Q. Here, P is the hypothesis of this theorem, P implies Q, and Q is the conclusion. A direct proof assumes P, the hypothesis, is true. And then you use various forms of valid argument to show that Q is true. And that would be called a direct proof. To get you started constructing proofs, let's develop a simple system. An integer n is called even. What is an even number? Well, even numbers are those that are multiples of 2. So 6 is even because it's expressible as 3 times 2. 22 is even because it's 2 times 11. So an integer n is called even if there exists an integer k such that n is 2 times k. So n can be expressed as a multiple of 2. What does it mean to be odd? Well, the odd numbers are only 1 unit away from the even numbers. N is odd if there exists an integer k such that n is 2k plus 1. Notice if I take any integer at all, like say 5, 2 times 5 would be 10 plus 1 is 11. I get an odd number. Two integers are said to have the same parity if they are both even or both odd. Otherwise, they are said to have opposite parity. So let's write down a conjecture. Show that if n, we'll assume it's an element of the set of integers, is odd, then n squared is odd. When you square an odd number, you get an odd number. And we want to do this using a direct proof. So our proof begins by assuming that n is odd. Let n, an integer, be odd. One of the joys of learning how to construct this kind of direct proof is learning that the way that we proceed is often indicated by the definitions of the words. What does it mean for n to be odd? Well, if n is odd, then there exists an integer k such that n is 2k plus 1. So how does this fact about n determine that n squared is also odd? Well, we'll just write thus: n squared is 2k plus 1 quantity squared. We need to FOIL out this binomial. Binomial is a mathematical expression having two terms. And we have a square of a binomial. The square of a binomial squares the first term, adds twice the product of the first and the last, and then squares the last term. Don't forget the middle term, which is twice first times last. If I have a plus b squared, it's a squared plus 2ab plus b squared. Don't forget the middle term. Now, I need to make this expression look a little bit more like this. So what we'll do is we'll group these first terms here and factor a 2 out. And we'll note that 2k squared plus 2k is an integer because of the closure laws of addition and multiplication for the set of integers. If you add two integers, you get an integer. If you multiply two integers, you get an integer. So I'm going to note that 2k squared plus 2k is an integer. So that means that n squared can be written as 2 times an integer plus 1. Therefore, we deduce then that n squared is odd. And that completes our direct proof. I might make the proof a little more elegant by saying set L equal to 2k squared plus 2k. L is an element of the set of integers because of the closure law of plus and times in the set of integers. Thus, n squared is 2l plus 1, so n squared is odd. Perhaps that clarifies it a little bit by showing that n squared can be written as twice some integer plus 1. Another common proof technique is proof by contraposition, i.e. using a direct proof of the contrapositive. If you have a theorem, P implies Q, an implication in this form, the direct proof would assume that P is true, and then from that, try to prove that Q is true. The contrapositive would be not Q implies not P. To prove P implies Q by contraposition, or using the method of the contrapositive, is to then do a direct proof of the contrapositive. You assume not Q, that Q is false, and then you use a valid argument to show that P is false, and hence not P is true. Here's an example. Show that if n is an integer and 3n plus 2 is odd, then n is odd. So we have a couple hypotheses here. First, n is an integer, and then 3n plus 2 is an odd number. Prove then that n is odd. So we have n is an element of z, 3n plus 2 is odd, implies n is odd. So that's the direction the implication goes as it's stated here. The contrapositive might be easier to prove. If n is not odd, then it must be even. Every integer is either even or odd. So if we assume the opposite of n is odd, and of course we're assuming n is an element of the set of integers, we're trying to prove then that 3n plus 2 is not odd and hence is even. So the contrapositive may be an easier theorem to prove. In fact, let's do that. If n is even, then n is 2 times k, where k is an integer. If that's true, thus 3n plus 2 will be 3 times 2k plus 2, and we have two terms here, 6k plus 2. These two terms have a common factor of 2, which we can pull out. 2 times 3k plus 1. Factoring a 2 from each of the two terms, we obtain this expression. What we find is that these 3n plus 2 can be expressed as 2 times an integer. That means that 3n plus 2 is even. And that is the conclusion of the contrapositive. That proves that the contrapositive is true. Consequently, we deduce that the original theorem is also true. Every logical implication is logically equivalent to its contrapositive. Why didn't we try a direct proof? Well, we'll assume 3n plus 2 is odd, which means 3n plus 2 is equal to 2k plus 1 for some k in the set of integers. Let's rearrange this and see if we can solve for n to somehow prove that n is odd. To do that, we need to subtract the 2 off. We need to isolate n. Whenever you solve an equation like this for a particular variable, you whittle away at the things surrounding that variable, starting with the thing that is furthest away by the order of operations agreement. And you do the opposite operation. So if 2 is added, then you subtract 2 on each side. And 1 minus 2 is negative 1. To get rid of the 3, we have to divide both sides by 3. It's unclear that you can express this as an odd number, 2 times some integer plus 1. How do you do that? It's unclear how to proceed. So a direct proof here ends up with a sad face, or maybe even a dead face here. We pooped out on this one. Don't know what to do to proceed to try to salvage this proof. Whenever this happens, you try to prove something directly and you end up lost like this. A good strategy is to turn to a proof by contrapositive or contraposition. Here's another example. Show that if n is equal to a times b, where a and b are natural numbers, remember that's the set 1, 2, 3, and so on in this course, then either a is less than or equal to the square root of n, or b is less than or equal to the square root of n. So let's try a proof by contraposition here. Here we take the opposite of the conclusion and try to prove the opposite of the hypothesis. The opposite of an or would be an and, because if I take the negation of a or b, I'll get not a and not b. So I'll have to assume, I'll suppose, a is greater than square root of n, and b is greater than the square root of n. That's the opposite of these two statements. I'll try to use these inequalities now to prove that this equation is false. But we know that if a is greater than root n and b is greater than root n, then ab will be greater than root n times root n, which is n. And therefore, n is not equal to ab. N will be strictly less than ab. And this will end the proof by contraposition. We're next going to turn to vacuous or trivial proofs. Suppose we're trying to prove P implies Q and P is false. If P is false, then P implies Q is true regardless of whether Q is true or Q is false. So when the hypothesis is false, the implication will be true regardless of the truth value of the conclusion. Here's an example. Suppose we consider the proposition if X is a discrete math student enrolled in section 4101, then X is a college student. I phrase it this way because this particular class is section 4W01, not 4101. In fact, Lone Star College Montgomery does not have a discrete math section 4101. So there is no section 4101, and X cannot be a discrete math student enrolled in section 4101. We deduce then that the theorem is vacuously true because there are no such students. Here's an example. Suppose n is a natural number, and n is a natural number between 10 and 15. If n is a perfect square, then n is a perfect cube. So here's the theorem we're trying to prove. But note n has to be between 10 and 15. And between 10 and 15, there are no perfect squares. Notice that 16 would be a perfect square and 9 would be a perfect square. 9 is 3 squared, 16 is 4 squared. So there are no perfect squares in this set, so the theorem is vacuously true. When is a theorem trivially true? Suppose you have P implies Q, and Q is true. Well, anytime Q is true, then P implies Q will be true regardless of whether or not P is true. So if you have some implication and you know the conclusion is true, then the theorem is trivially true. Let me give you a classical definition of what we mean by an open set in the real numbers. We say that S is open if for each x within S there exists an r greater than 0. It may be quite small, but there will exist such an r such that the interval x minus r to x plus r will be a subset of the set S. So we have a little open interval around each point in the set, and that open interval lies entirely within the set S. As an example, suppose I have the numbers between, say, 1, 2, 3, 4. We're going to take these numbers and these numbers to be our set S. How do I know it's open? If you choose any point in there, you can always put a little small interval like this around it that is entirely contained within the original set S. Therefore, this set is open. If we had filled in one of the little dots over here, then it would no longer be open. And that's because no matter how small you make that radius, you're going to have points that lie outside of the set S within that interval. And so if you throw in an endpoint, it's no longer open. So clearly, any interval AB is open as long as it does not contain the endpoints. This if you contain the endpoints, this is not open. You can take open sets and take their union, and like over here when we started out with a hole over here, if you take the union of two open sets, you end up with an open set. Clearly, if you take S to be the entire real line, you can always put an interval around each point that lies entirely within the real line, and therefore the entire real line is open. So everything from minus infinity to infinity, this forms an open set. That's kind of an extreme case. There is another extreme case. What about the empty set? Is the empty set open? So that's the question I really wanted to address in bringing up all of this machinery here, is the empty set open? And the answer is, for each x within the empty set, you can choose any radius, and this interval will lie within the empty set, because there do not exist such x. There is no x in the empty set. So if there were an x in the empty set, you could fit the interval within the empty set, but there are no such, which means it is vacuously true that the empty set is open. Here's another example. Here's a conjecture. If n is a natural number, then n squared is greater than or equal to n. So we could try this out for a few examples. Say n equals 2. 2 squared is 4, and 4 is bigger than or equal to 2. So what about n equals 0? Is it true there as well? N equals 0 is traditionally not an element of the set of natural numbers, though your text may differ. But is this theorem still true when n is equal to 0? And 0 squared is 0, and that is bigger than or equal to 0. Therefore, this theorem is trivially true. Well, the implication, n squared bigger than or equal to n, for n equals 0. What is a rational number? Is it a number that talks and makes sense? I always have to give the bad jokes. However, a rational number is a number that can be expressed as the ratio of two integers. If r is an element of the set of real numbers, we say that r is rational if there exists integers p and q in the set of integers, q not 0, such that r can be expressed as the ratio p divided by q. So p and q have to be integers, like 2, 3, -4, whatever. But it can't be something like the square root of 2. So p and q will be integers. Notice that pi divided by 2 is not rational. Pi is not a rational number. Otherwise, if r cannot be expressed as the ratio of two integers, r is irrational. It took a long time for mathematicians to prove that pi is not rational, but the proof does exist. But remember, definitions are where we begin by exploring new relationships. We have a new term here, what it means for a real number to be rational. Now we can use this new concept, this new notion, the rational number, and explore other relationships and possible theorems. Here's an example. Prove that the product of two rational numbers is rational. So in our proof, we'll do a direct proof. We'll let R1 and R2 be rational numbers. Then there exists P1, P2, Q1, Q2, so that R1 is P1 over Q1, R2 is P2 over Q2, where P1, P2, Q1, Q2 will be integers, and Q1 is not 0, Q2 is also not 0. Then R1 times R2 will be P1 over Q1 times P2 over Q2, which can be expressed as P1 times P2 divided by Q1 times Q2. You multiply fractions straight across. By the closure law, P1 times P2 is an element of the set of integers, and so is Q1 times Q2. And since Q1 and Q2 are not 0, this product, we'll call this P hat, and we'll call this product Q hat. We'll know that Q hat is not 0 because it's the product of two non-zero numbers. And so that we have R1 times R2 expressible now as P hat divided by Q hat, where these two things are integers, Q hat not 0. From this we deduce then that R1 times R2 is rational. That'll be the end of the proof right there. We arrived at this from the closure law. If you multiply two integers, you get an integer. So we made that a note of that, and we gave it a notation then as P hat for the product and Q hat for the product of the Q's. We could then write the product of the original product here, R1 times R2, as this ratio of two integers. So it's rational. There's another important type of proof that you need to be aware of. It's called proof by contradiction, or sometimes reductio ad absurdum. Suppose that we want to show P implies Q. I want to prove this is true. The way that the proof by contradiction goes is you assume P is true and Q is false. You assume that the conclusion to the theorem is false, where the assumptions are assumed to be true. The hypotheses are assumed to be true, conclusion false. You then construct a sequence of arguments to arrive at some proposition and its opposite to be true. This is a contradiction. Something is true and it's not true at the same time. Whenever you use this method, Assume that the hypothesis is true and the conclusion is false. You can construct a sequence of arguments to arrive at some statement is true and it is not true at the same time. That means that you've made an assumption that is bad. Somewhere along the line before that, you had to have made some false statement. But we are assuming that we're using valid arguments, a sequence of valid arguments, to arrive at this contradiction. By the way, the contradiction symbol is two arrows colliding like that here. So the only thing that is possibly false would be that our assumption that Q is false. This is this suspect here. How did we arrive at the contradiction? By making a false assumption. It's fair to assume the hypotheses. What's not so fair is to assume that the conclusion is false. If, when we assume the hypotheses are true and the conclusion is false, and we arrive at some kind of contradiction through a sequence of valid arguments, then this must have been wrong. We deduce then that Q is true, and that completes the proof that P implies Q. So this proof by contradiction, it's a little bit different than proof by contraposition, the contrapositive. There you assume not Q and you try to prove not P. For a proof by contradiction, or a reductio ad absurdum proof, you assume that the hypotheses are true but the conclusion is false. Then you arrive somehow at some contradiction, and so your conclusion must in fact be true. A classic proof by contradiction is a theorem that was first discovered by a man named Hippasus of Metapontos. Now, Hippasus was a member of the Pythagorean Society, so he was a student of Pythagoras, and he discovered that the square root of 2 is not rational. How do you prove that the square root of 2 is not rational? The way that we'll proceed is a proof by contradiction. We'll assume the opposite of being not rational would be rational. So that's the opposite of the conclusion that we're trying to make. The square root of 2 is rational. What does that mean? Well, rational numbers are numbers that can be expressed as the ratio of two integers. P and Q are elements of the set of integers, and Q is not 0. Notice you can always reduce a fraction. And when the fraction is reduced, if I had something like 4 over 6, 2 goes into here twice, 2 goes into here 3 times, we can reduce the fraction 4/6 to 2/3 by canceling out any common factors. Let's assume that that process has already been done, and P and Q have no common factors. We'll take this equation and square both sides. And then we'll multiply both sides by Q squared. We'll get P squared is equal to twice Q squared. From this we deduce that P squared is even. It's a homework problem to show that if P squared is even, then P is even. After all, the only source for a factor of 2 in the perfect square would be from a factor of 2 in P to begin with. And what does it mean for P to be even? That means P is 2 times K, where K is an element of the set of integers. Even numbers are numbers that are multiples of 2. But now, we'll come back here to this equation, p squared equals 2q squared. P is equal to 2k. So 2k squared is 2q squared. But the left-hand side is 4k squared, and the right-hand side is still 2q squared. We can divide a 2 off on each side. As long as you do the same thing to both sides of an equation, it remains an equation. And we get q squared is 2k squared. But that means q squared is even too. Now that we know that q squared is even, we deduce that q is even. So that q is 2 times L for some L that is in the set of integers. But this contradicts the fact that P and Q have no common factors. Suppose P and Q have no common factors, the fraction is reduced. Which means this contradicts the assumption that P and Q have no common factors. There's your contradiction. Because we have a contradiction, some assumption that we've made is false. But the only assumption that we've made that could possibly be false is our assumption that the square root of 2 is rational, that it can be expressed as the ratio of 2 integers. Therefore, root 2 is irrational. And that's the end of the proof. This beautiful little proof was constructed by Hippasus of Metapontos, a member of the Pythagorean Society, sometime about 500 BC. When he did this so upset his contemporaries because it completely upset their understanding of the entire universe. Pythagoras had taught for a long time that if you study anything deeply enough, it reduces to a question of the proportion between whole numbers. In other words, if you study anything deeply enough, it ends up resulting in a fraction. As an example, when Pythagoras studied the musical scale, he actually invented the musical scale by forming fractions of the string. However, Pythagoras didn't stop there by just inventing the musical square, by inventing fractional ways of pressing the string to arrive at nice sounds. He also assumed that the planets were on these crystal spheres that circled the Earth, and that the radii of these crystal spheres was such that if you were to ring the spheres, they would make a harmony, the harmony of the spheres. And as a consequence, Pythagoras felt that the distance between the various planets had to be fractions. So, as with everything else with Pythagoras, if you study anything deeply enough, it ends up resulting in a fraction. But here, Hippasus of Metapontos, a member of the Pythagorean Society, a student of Pythagoras, is able to prove that the square root of 2 cannot be expressed as a fraction. It cannot be written as the ratio of 2 integers. It is not a rational number. So this upset their understanding of the entire universe. So what do you suppose they did to poor Hippasus of Metapontum? Well, my students usually assume that they go straight to they killed him. And there are several different possible myths about what happened to Hippasus. One of them is that they took Hippasus on a one-way fishing trip into the Mediterranean. So yeah, they killed him. But another one of the myths is that instead of killing him, they set up a tomb for him and desecrated the tomb so that he could see his own tomb being desecrated. Well, Whatever the case is, whether they killed Hippasus or not, it's clear that this upset them, and they had a strong negative reaction to this proof that the square root of 2 is not rational. But there it is, one of the first proofs by contradiction, historically as well as in this class. But proof by contradiction is a very common proof technique used in mathematics and also other deductive sciences. In our next example, we'll let n be an integer. Then n is odd if and only if, so the implication goes both ways, n squared is odd. This is an if and only if kind of statement, but we can still prove this by the contraposition. We'll assume the opposite of one side. Both sides are going to be if and only if the other. So let n be even. Then n is equal to 2 times k, where k is an integer. That's what it means to be even. Thus, and we can say this is true if and only if, when we square both sides, we'll get n squared equals 4k squared, which means n squared can be written as 2 times 2k squared. We'll set L equal to 2k squared, and note that L is an integer by the closure law for multiplication of integers. So n squared is 2 times L, and that just means that n squared is even, and that goes both ways. These implications go in both directions. So we have then that n is even if and only if n squared is even. By contrapositive, we deduce that n is odd if and only if n squared is odd. How do you prove a theorem is false? How do you do that? One method is by providing a counterexample. It takes only one case, just one case of the conclusion of the theorem being false, is enough to show that the entire theorem is false. All you have to do is exhibit one counterexample, and then the whole theorem is blown up. It's not a theorem, only a false conjecture. A natural number is prime if it can only be divided evenly by 1 and itself. There are no other factors that divide into it evenly. So, for example, 2 is prime. It's only divisible by 1 and 2. 3 is prime, divisible by 1 and 3. 4 is not prime because it's divisible by 2. 5 is prime. 6 is not prime. It's divisible by both 2 and 3. 7 is prime. 8 is not prime. 9 is not prime because it's divisible by 3. 10 is not prime, but 11 is prime, and so on. Suppose I have a conjecture that 2 to the n plus 1 is prime for each n in the set of natural numbers. Well, let's look at some examples. 2 to the 1 plus 1 is 3. 2 squared plus 1 is 5. So far, so good. 2 cubed plus 1 is, well, 2 cubed is 8, plus 1 is 9. Wah, wah, wah. The theorem's false. There's my counterexample. And so this is not true. What are sources for common errors in proof? Well, the classics are bad algebra or arithmetic. But those are not the only possibilities. Another is something called a non sequitur, which in Latin means it does not follow. This usually happens when you assume something is true, but it's maybe not necessarily true. And so you use that false assumption to prove the theorem. So you make a bad inference. So most non sequitur forms of errors occur when you insert certain statements that are not fully justified. Here's an example of an erroneous proof. Suppose I have the theorem that 2 equals negative 1. And this is my proof. Suppose A equals B. If A equals B, that's fine. We can multiply both sides by A, so I get A squared equals AB. And I'll multiply both sides by 3. So 3A squared equals 3AB. So far, so good. We'll break each side up as follows. 2A squared plus A squared equals 2AB plus AB. One of them plus 2 of them makes 3 of them. Same thing over here. Now we're going to move things around a little bit. I'll have 2A squared minus 2AB equals negative A squared plus AB. We can now factor each side. I'll factor 2A out on the left. So I'll have 2A times the quantity A minus B. On the right-hand side, I'll factor a negative A out. And I'll get negative A times the quantity A minus B. Notice we get a minus here because if we were to distribute this back, we'll get a negative A squared, and negative times negative makes a positive AB. So now, what happens if we cancel off common factors on each side? We can deduce that 2 equals negative 1. So, does this constitute a valid proof? Or did we make a non sequitur in there someplace? Well, since 2 does not equal negative 1, you know that we had to have done something badly here, though most of these steps are perfectly justified. The step that is not justified is the cancellation of A minus B from both sides. If you go back up to our original assumption, we have A equals B, which means A minus B is in fact 0. The only way to cancel a factor from both sides is to divide both sides by that common factor, but you cannot divide by 0. It's still true at this point. 0 equals 0. Once you cancel off a 0 from each side, I mean, this is a true statement. 3 times 0 equals 4 times 0. That's true, but you can't cancel zeros off because that would imply that you could divide by 0, and that's not defined. So the cancellation here was the non sequitur. It does not follow that you can cancel because A minus B is 0. So this proof is hogwash, though it is a good one for you to remember. You can fool all kinds of people with this particular proof. In our next example, I'm going to ask, what is wrong with this proof? The so-called theorem is if n squared is greater than 0, then n is greater than 0. And this seems rather dubious, since we can easily prove that this is not true by using n equals -1. N squared, -1 squared, is 1, and 1 is bigger than 0, but -1 is not bigger than 0. It's less than 0. So one counterexample is enough to prove that this is false. But here's the proposed proof. The proof, so-called proof, goes like this. Suppose n squared is greater than 0. Since it is true that if n is greater than 0, then n squared is greater than 0, we conclude that n is greater than 0. That's the end of the alleged proof. Well, you're taking this implication, positive numbers have positive squares, and you're trying to reverse the implication. That's the converse, but the converse isn't true. So this is a non sequitur because you've chosen to claim some implication going one way, and then concluding the implication goes the other way to give you n greater than 0. The problem is the conclusion right here. You cannot conclude that from this. This is one of our fallacies, called affirming the conclusion. And here we have P implies Q, Q therefore P, Q therefore P. And this is a fallacy. This is something that doesn't work in logic. If you assume the conclusion is true, that doesn't mean that the hypothesis is true at all. So, in any case, yes, while this may be a true statement, you cannot conclude from that the hypothesis is true just because the conclusion is. That's affirming the conclusion. What is wrong with the following proof? Here's our quote theorem. If n is not positive, then n squared is not positive. Well, we could again prove that this theorem is false by one counterexample, n equals -1. -1 is not positive, but -1 squared is +1, and that is positive. So that would be sufficient to prove that this is false. But the argument provided in the form of a supposed proof is, if n is positive, n squared is positive. We conclude, since n is not positive, that n squared is not positive. And that's the end of the supposed proof. You can see here that what we've stated down here, if n is positive, n squared is positive, is it's not the contrapositive of the original theorem, it's called the inverse. If I have P implies Q, the inverse is not P implies not Q. And n is not positive versus n is positive. This is the negation of this statement up here. This is the negation of the conclusion up here. So what we're looking at here in this instance is not the original theorem, it's the inverse to the original theorem, which is true. However, because n is not positive, the opposite of this, that doesn't mean that n squared is not positive, the opposite of the conclusion over here. So what is done wrong? We have this theorem that we're trying to prove. We have the inverse, which we actually think is true. But we're taking P and then concluding, therefore, Q. This is denying the hypothesis. Normally it's written like this. P implies Q, not P, therefore not Q. That's an invalid form of argument. It's a logical fallacy called denying the hypothesis. You take the opposite of the hypothesis, which is what we did here by assuming P, and getting the opposite of the conclusion, which is what we did here by getting Q here instead of not Q. So that's an invalid form of argument. Another fallacy is sometimes called begging the question. Maybe an easier way of understanding this is assuming the conclusion. So if you're trying to prove P implies Q, and the proof goes, assume Q is true, therefore Q is true, and assuming that that's the end of it, that's not a valid form of proof. That doesn't show that for different possible truth values of P, that P implies Q will always be true. Surely, if Q is true, then the implication is true, but you can't assume the conclusion. You wouldn't believe how easy it is for even a professional mathematician to make this sort of logical error, assuming the conclusion. I myself have found myself guilty of this at times. This is a form of circular reasoning, because you're basically saying Q implies Q, which implies Q, which implies Q, and so you're not getting anywhere. So in our next example, I ask, is the following correct? Is it correct reasoning? Here's the supposed theorem. If n is even, then n squared is even, which happens to be a true theorem. Here's our alleged proof. Suppose n squared is even. Then n squared equals 2k, which implies that n equals 2l for some l, and that implies n is even. End of proof. So here, we're assuming the conclusion. Suppose n squared is even. Well, that's begging the question. That's assuming the conclusion. So that means that this proof is bogus.